Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing three topics and the pattern was DFS traversal. So let's solve the next question, which is print all nodes at distance k, and which is very important from the interview perspective as well. So let's read the problem statement. It says we will be given the binary tree and the value of the target, okay, and an integer k also. We have to return an array of the values of all the nodes that have a distance k from the target node. So we will be given a target, and from that target we have to traverse k distance in all the directions, all are allowed, and we have to consider all those values in our resultant array. So from 5, as you can see, from 5 we can go on 2 and 7, 2 distance. Similarly, from 5, 2 to 4, 2 distance. So 7 and 4 will be the answer. Similarly, in the upward direction also, from 5 to 3, 1 distance, and 3 to 1, 2 distance. So as you can see, 7, 4, 1 will be our answer. Talking about the constraint, it says the number of nodes can go till 500. The constraints are very small, so we can think for the linear approach, n square, all over works, right? So whatever possible, we will do that. But the main concern is that we know in a binary tree, from the parent to the children only we can traverse. We cannot go back, correct? Remember? So from 5, 2 distances, so we can travel in towards the downward. But what about the upward direction? How can we traverse this? If we are able to crack this point, then definitely the code will become easy for us. But how to crack this? Okay, so to go towards this side, definitely we cannot change the direction of the tree. Don't think about that. We can change the direction. It's not required. If for any node, okay, for any node, we from any node we can go to the children without any storage or anything, correct? By default we can go to the children's. But from node to parent it is not allowed. So why not to do one thing? For every node, store their parents. Why? See, from parent, from the node to parent we cannot go, but we can store the relation at least. Means for 5 node, what is my parent? 3. So we can directly jump onto that node. That we can do, correct? Okay. So what will happen? Initially, first we have to start from the root node. And what I want is for every node, just give me their parents and store it in any data structure. So when we want to store one node with one node, so definitely we go with HashMap, right? Key and value pair. So for 3, we don't have any parents, so we will store null. Now we will go on left side and right side for every node I am saying. So when we will go on left side or right side, in the parent we will send 3. Can I say that? Yes, because for 5 and 1, the parent is 3. Okay. So now when we'll encounter 5, we'll save parent 3. Now when we'll encounter 1, we'll save parent 3. Correct? Now again from 5 we'll go to 6 and 2, and the parent will be 5. Correct? So again for 6, the parent is 5, 2, parent is 5. Correct? Similarly for 0, parent is 1, and for 8, parent is 1. Now similarly for 7, parent is 2, and for 4, parent is 2. Done. So we have to make a function. Let's make a function here. Okay, let's call it build parent function, and there we have to send the root also and their parent also. Done. First we have to check the base case the root should not be null. Root should not be null. Okay, then we will return. So if root is null, we will return, or else what is our task? Whatever we have, this is map, correct? So in map we have to put, what we have to put? For root we have to put the parent. That's it. So what will happen? Initially we have 3. So for parent 3, yes. So what we have to put? In the map we'll put for root, which is 3. So for 3 we'll put the parent. So initially the parent was null. That we'll send while calling this build parent function. Okay. So we'll save it. Now what is our task? To go towards the left side and right side? Yes. So what we'll do? We'll call the same function, which is build parent. Build parent. We will send root dot left child, and parent will be root for it. Correct? Similarly, we'll send build parent root dot right child and root as parent. That's it. So only this much build parent DFS call will help us to fill this relation. But the question is ki why we wanted to fill this? We want to fill this because suppose we want to start from 5. Suppose we want to start from 5. So now what we will do? We have to traverse all the direction nodes of distance 1 first. Can I say that? So downwards so we can go without even storing their children's. Why? With node dot left and right. But how to go for upward? That is not possible because direction is not allowing us. So for that only, so that we can go upward, we have maintained a map, parent map. So what we'll do in the map, for the node, we will get the parent which is 3. Okay. Why we have to store this? Because for a distance 1, what the question says, ki give me all the nodes which are at distance 2. Forget about distance 2. What if it was distance 1? Then you have to travel in all the directions. So for the children, you can go for left side and right side, dot left, dot right. But how you will go to the parent? So for that, we have maintained the map. So we will just read the value. What's that? 3. Okay. So now in another data structure, we'll save 6, 2 and 3. So these are the nodes at distance 1. But wait, we have to go for what? Distance 2. Can I say that? So it means we have to travel 1 distance again from all these nodes. Correct? So we'll pop this and then we'll get their left and right children. So for 6, we don't have any children. Now we'll pop 2 and we'll get their left and right children. Because suppose if left has also, like 6 has the children, suppose 0 and 1. So don't you think 0 and 1 will also be considered the children's at distance 2 from the node 5? So that is why whatever we have stored, we have to pop 1 by 1 and get their children's. So 6 does not have any children. 2 has children. Yes, 7 and 4 will store. Now 3, does 3 has child? Yes. Again, along with children, we have to look for the parent also. Okay, that's what we did for 5. In case of 5, what we did? We stored the children and the parent. Remember? So for 6 also, we will store the children, but children is not there. But we will store the parent also. But don't you think, if again you will store the parent, so 6 will say, see, 6 will say, ki hey, 1 distance beyond me, I am getting your another child with distance 2. So from 5 to 6 and from 6 to 5, it is saying, yes, I found a child at distance 2. But do you think it is valid? I don't think so. So what we should write extra, that we won't come at the same node which we have already visited. Can we maintain a set data structure? We can say ki yes, initially we started with 5 na, so 5 is already visited. Now don't come again here by any node. So when we went on 6, we maintain all the children of 5 and the parent. Then we pop 6, that's what we'll do. Let's write it. 6, 2 and 3 will be their just next child. Children means you can say ki K for K1. Now for K2 what we will do? We will pop 1 by 1. We'll pop 6. We'll get the children of 6. Left child, right child and null. Okay. Parent will go in the map. Parent of 6 is 5. But 5 is already visited. In the visited or set, we'll check. Here we already have 5. Okay. Don't insert it. So for 6 we don't have anything at a distance 2. Now from 2 we'll check, do we have children's? Yes. So 7 and 4 will insert in the next iteration. Okay. What is the parent for 2? So for 2, the parent was, we stored 1, right? Okay, my bad. Here we should have stored 5, right? Parent was 5. Yes. So parent was 5. But this node is already visited, so we'll not store this. So again, for 2 we have only stored 7 and 4. Now, next time we'll pop 3. Now for 3, do we have parent? For 3 we have, but it's null. Okay. Do we have children's? Yes. Left children? Yes. But left children was already visited, so we'll not go there. Right children we have? Yes. So store it. So we'll store it. So again, here at like k is equal to 2, whatever we have, this is what the expected answer. Correct? So that's what we have to do. So what do you think? From like first of we know na ki we don't have to start from root. We have to start from the target, from where we are expected to return. Why you are thinking to travel first and search if node is equal to target when we can simply start? Why we can simply start? Obviously, because if we will start from any node, any random node, where we want to go? Children's, okay. From there also you can go to children. Parent, okay. Parent, so you were earlier also not allowed to go. For that only you maintain the map, right? to store their parents. So even if you are starting from the target, then and there, instead of starting from the root, you can go and find the parent from this map, right? So hence it's not needed to start from the root and check all the values until it matches with the target and then starting the real iteration, correct? Okay. So now we have to start from the target node, which is 5. Okay. Now whatever we did now, what we did? Went on to the children and parents and we stored in a data structure. Don't you think it's nothing but Q data structure? Yes. So this thing we can achieve using the BFS traversal. Okay. And after every level iteration, level you can say children at distance 1 1 is also 1 level and parent is also 1 level. So what we'll do is, let's remove this. We will start with the target node, right? So I'm assuming that with the build parent function, we'll be able to build this map. Now we have to start with the Q data structure. So first we'll construct the Q data structure, and in the Q, first we'll insert the target, which is 5. As a node we'll insert, right? Now until our Q is empty. So while our Q is not empty, until we have the values in the Q. Now what we'll do? We have to pop, yes. But do you think we should randomly pop all the elements, or we should pop as seeing how many number of elements we have in that level? Considering now the level order traversal says ki we will have the children's also and the parent also, correct? So definitely we have to calculate the size. So size we will calculate Q dot size, yes, and now we'll run the for loop for that many size. So now we have to pop. So let's say in the current we'll pop Q dot poll, correct? Now after popping, what is our task? Once we have popped, okay, we have to check ki does our K matched, because K was initially 2. So you have two options, either initialize a new variable, let's say distance, and keep incrementing it and check if distance matching with K, or else decrement the K, decrement it until the K becomes 0. You cannot say you have reached out. Okay. So I am initializing a distance variable here with 0, and now my task is to check if distance matches with my K, correct? But where should I check? Do you think we should check after every levels or inside it also? Obviously after every level, because after every level means this is in one level, right? So after this level only you can say na increment my distance, correct? So hence here, like before this calculation of size and all, first task is ki check ki what if our current distance is matching with K. If it is so, then break. Break means come out of this Q, and whatever will be there in my Q data structure, that I will return. That we'll see. Let's see. First let's maintain the Q data structure somewhere here. Okay, here is our Q, and initially in the Q we have 5 as a node. Now here we checked if distance matches. Initially distance is 0, K is 2, no, it does not match. So we'll calculate the size, and that many number of times we have to run the for loop. Now here what we'll do, we'll pop the value from the Q. Once popped, our task is to add their children's left and right children and their parent. Can I say that? So left child I can only add if the left child exists and if it is not in the visited, right? So in the visit, like we have to make a visited set also outside. So considering here we would have created hash set of type tree node, right? Because we are going to store the nodes only. Let's say visited. Okay, new hash set. Okay. Now here what we'll do, we'll check ki if my root dot left is not null. Ki if my left child is not null. Along with that, we have to check ki if that left node is not present in the set, correct? So we can check by adding this left node in the set. Ki if it adds means it returns true, means it was not there. What I said, in visited, please add root dot left. What? Root dot left. If it's added, then it will return true, means it was not earlier, correct? So what our task? Our task is in the queue, please add what? Root dot left. But we popped as current, right? So here instead of root, we'll write current. Okay. Here also current dot left. So in the queue, what is our task? Add current dot left. That's it. Similarly, we have to do for right child also. Ki if current has right child, means if it is not null, and also if we will add in the visited, in the visited set, we will try to add current dot right. If it gets added, means it was not earlier there. If it is so, then in the queue, please add current dot right child. Done. This was like we have added what? First we popped from the queue, okay, and now we have added what? Children, 6 as a left child and 2 as a right child. But we have to add this node also, and where it is present in the map. So how should we read? How should we read? First we have to check ki if what? Map dot get 5. So with 5 from the map we'll get the parent. We'll try to check if the parent is not null first, and once it is not null, then we'll add this again in the set. If it gets added, means for sure it was not there. Okay. So what we'll write ki if map dot get with what? With current. So we'll get the parent if it is not null, and also in the visited, if we will add in the visited, what we'll add? Map dot get for current. So we'll get, like, map will give us parent, right? So map will give us parent. So with the help of current, we'll get the parent. We'll try to add in the visited. If it gets added, it means earlier in the set parent was not added. Means we can add it now. So again, what we'll do, in the queue we will add, but what we'll add? What we'll add? The parent. Where is the parent? Can I say map dot get current? That's it. So what we did, these 3 lines of code will help us to add all these 3. Now after coming outside the for loop, can I say ki all these numbers were at k is equal to like one more distance. So can I say distance plus plus? Correct. Now again we'll go upside here. Is our queue empty? No. Distance is 1. K is 2. So whatever children we have now, it is at distance 1, not 2. So we'll not break. Again we'll calculate the size. Size is 3. Now we'll run for 3 times. Okay. Now we'll pop the very first node, which is 6. Now we'll check, does it has left child? No, it does not. Does it has right child? No, it does not. Now we'll go in the map and get the parent of 6. Parent of 6 is 5. Okay. Is it null? No. Try adding in the visited array. If you will try to add it, like a hash set will not allow it to add, and it will return false. It was not get added. Correct. So as it is false, because of the AND operation, true and false will return false. So this if case will not run. So in the queue we will not add 5 as a children or parent. Correct. Yes. So 6 will simply popped. Now next time what we'll remove? We'll remove 2. Correct. Now we'll check their children's left and right. Do they exist? Yes. Are they present in the visited set? No. So we'll add. What we'll add? We'll add their children in the queue, 7 and 4. Done. Now we'll remove 2. So now we'll pop 3, and once we pop 3, we'll see for their parent. Parent is null. Left child is present. But when we'll try to put this 5 in the visited, it will not get added because 5 is already there. So hence we'll get false. So we'll not add this in the queue. Now right child, yes, it is not there. Means not there in the visited array. So we will add this in the array, which is queue. Sorry. Okay. So we have popped for 3 times because earlier for loop was supposed to run for 3 times. Okay. Now this is what we have in the queue. Now coming outside this for loop, here we'll increment the distance, and now the distance will become 2 instead of 1. Correct. Again we'll go there. Queue is empty. No, it is not empty. So now we'll check, is the distance, which is 2, matching with k? Yes. So break. Break means come outside this while loop, and now whatever you have in the queue data structure, iterate through it and get all the numbers like nodes and read the nodes values, which is 741, because in the queue to you stored node. Correct. You have to return integer. So read all the values and return it, and that's it. Very simple. So can we write the code for this? So here is the code what we have discussed. First we have to create the hash map outside the main function so that it will be globally defined. Now we have to call the build parent function. Build parent is nothing but it is simple a DFS function where we are checking the base case, and in the parent hash map we are inserting the root first and then their parent. Okay. And now when we are calling for left and right side, the parent we are sending as the root. Okay. So this build parent function will help us to fill the hash map with the parent. Now we'll make the set and the queue, and first in the queue and the set, as we are starting from the target which is 5, so we have to insert it first. Now distance we will initialize with 0 because we are incrementing after every level. Now until it becomes empty, first check ki what if your distance matches with k. If yes, then come outside the while loop, or else calculate the size and run the while loop or for loop for that many number of times. So for that many number of times, our task is to pop that node, done, and insert the left child, right child and the parent. So left child should not be null and should not be present in the visited array, then only add in the queue. Similarly, right side should not be null and should not be present in the visited array, then only add in the queue. And the parent should not be null and should not be present in the visited array, then only in the queue we'll add this. So instead of only inserting left and right child, we have to insert the parent also, because we cannot go upward direction, so we have maintained the hash map earlier. That's it. And after every iteration of while loop or for loop, you can say, after that you have to increase the distance, saying ki after every level you can say ki yes, one distance you have covered in the breadthwise. Done and done. And after this, if at any time we can say ki if distance matches with k, come outside this. And as you saw in the dry run ki 741 was present in the queue, so after coming outside we have to create the integer list answer, and until the queue becomes empty, from the queue we have to pop and store the value of it, because in the queue we had stored the nodes. And that's it. Let's run the code. Talking about the time complexity, first of all, this build parent function we run for O of n times to make that hash map. Can I say that? For every node we stored parent, so obviously at every node we had reached out, so O of n for this. Now plus extra further O of n. Why plus, not multiplied? Because they are not in nested order. First we called the build parent function, correct, and then only we are starting our queue while loop. So in the while loop again we are traversing until we are finishing all the nodes. Why I am saying all the nodes? Because what if in the worst case it says k can go till the number of levels. So in that case, so you will end up iterating all the nodes until you reach that k, which is the height of the binary tree. Here so it was only 2, so it stopped. But what if let's say k was 3, then so you will end up iterating till 8 na, from 5. So in that case, so you have encountered every node. So you can say O of n, further O of n for the actual answer preparation. So O of n plus O of n, which is total 2n, correct, which is linear only. Space wise we have created the extra hash map O of n. Now the DFS call also would have maintained their inner stack call that further takes height of the binary tree, which is O of h, correct. And the while loop here, q, for q also and for set also you can say ki yes, O of n. So total 3n plus O of h, as n is greater, so you can say 3n, which is linear O of n. So let's submit this code. This was your code using BFS and DFS, because we have applied DFS to build the parent and BFS to store all the nodes at distance k. So if you understood, this was your code in Java. Here is the code in C++ with the similar approach. If you understood that, you can definitely write this on your own. And here is the code in Python if you understood and if you are from Python background. So if yes, you understood all the approach, why we maintained the hash map to store the parents, because we were not able to travel back or travel upward. Instead of changing the direction, we prefer to store it. If yes, then definitely you are eligible to go in the sheet and mark that question from that sheet. And you are done. Also guys, please do let me know in the comment section that yes, you understood or you submitted. And also if you like the video and like the way of explanation, please do hit the like button and subscribe the channel if not yet subscribed, because that gives me more motivation to make more videos for you all. And that's it. I will attach the link of the sheet and my social media. You can even share your progress of Rising Brain with me on social medias. Let's meet in another video with some more interesting questions, topics and patterns. Till then, keep learning, take care of yourself and your family.